Hi to all. Today we are going to discuss about magnetic measurements. Magnetic measurements, the syllabus regarding Unit 5 magnetic measurements is ballistic galvanometer, equation of motion, flux meter, construction details, and comparison with ballistic galvanometer, determination of BH loops, method of reversal, 6-point method, AC testing, iron loss of bare samples. This is the syllabus regarding magnetic measurements. In the starting, what are the instruments we are using for magnetic measurements? Those we'll discuss. After that, we will enter into the syllabus, that is magnetic measurements. According to syllabus, let us start galvanometer. Galvanometers we are using in DC bridges and AC bridges. In DC bridges we are using ballistic galvanometer, whereas AC bridges we are using vibrational galvanometer. What is a galvanometer? A galvanometer is an instrument used for detecting small current or voltage in a circuit. Galvanometer the galvanometer we are using to detect a small current or voltage in a circuit. In case of bridges, we are using galvanometer. When the bridge is in balanced condition, the galvanometer does not show any deflection, hence the bridge is balanced. Very small current, 0 amps, will flow through galvanometer when the bridge is in balanced condition. A galvanometer measures the magnitude of current which enters or voltage between two terminals. Between two terminals of galvanometer, what is the voltage or current? If any current enters, the galvanometer shows deflection. Basically, galvanometer measures the magnitude of current. If the voltage is applied to the galvanometer, based on proportional to voltage, a current will enter to the galvanometer. The main application of galvanometers are indicate zero current in bridges and potentiometers. That is, the galvanometer main purpose is to indicate zero current in bridges and potentiometers. As you know that there are so many applications of DC bridges and AC bridges. In Crompton's DC potentiometer also we are using galvanometer to show null condition. Null condition in the sense the current is zero. If any small current enter to the galvanometer in Crompton's potentiometer, it gives a small deflection. If the deflection is observed on the galvanometer G, then the bridge is in unbalanced condition or potentiometer is unable to read the value. That means the potentiometer is not measuring accurately. If the galvanometer shows zero condition, null condition, then only we are taking the readings from the dial settings. Now let us start the d'Arsnoval galvanometer. D'Arsnoval galvanometer is very commonly used in various methods of resistance measure and also in DC potentiometer. The construction of D'Arsnoval galvanometer will show you first. Instead of that, the D'Arsnoval galvanometer construction is this one. It is similar to PMMC instrument. It consists of two magnets N and S. A mirror is attached D'Arsnoval galvanometer to read the value. Upper suspension is provided with flat ribbon. There is no controlling torque actually in galvanometer. Hence the galvanometer easily deflect the mirror pointer when it moves. If you shake the galvanometer, easily the pointer will oscillate. If you shake the galvanometer by the hand, easily the pointer will move. Very sensitive instrument the galvanometer is. Similarly, the construction of D'Arsnoval galvanometer as shown in figure. It consists of a moving coil, permanent magnets, iron core and suspension. It is similar to PMMC instrument except the springs. Springs are absent in D'Arsnoval galvanometer. According to syllabus, ballistic galvanometer or D'Arsnoval galvanometer both are same. The flux meter, in the sense flux meter also, it will be same. Construction will be, but small modifications are there. Those modifications we have to remember. I will tell you what are the modifications in ballistic galvanometer and flux meter. The differences also I will explain. The moving coil, it carries the current. Similarly, PMMC instrument, the moving coil carries the current. When current flows through moving coil, a deflecting torque will be produced because deflecting torque TD is proportional to I. in case of moving coil instrument. The construction is like this. The coil is suspended so that it can freely move about its vertical axis of symmetry. It is mounted on metal former. The former is using a metal former. Based on that, it is eddy current damping is possible. It is placed in uniform radial horizontal magnetic field between two poles of permanent magnet and iron core. It is the purpose of moving coil is to carry the current to show the deflection. But constructionally, there is no controlling spring. Later on, you can understand that. Iron core. The iron core is a spherical in shape. If the coil is circular but it is cylindrical, if the coil is rectangular, the iron core is, if the coil is circular, it is in cylindrical, the iron core will be. Similarly, if the coil is cylindrical, the core will be rectangular. That is the purpose of iron core. Iron core purpose is similar to DC motor. You can see this iron core is this one. This is the iron core for a directional galvanometer or ballistic galvanometer. Again, I am telling that it is not a directional, ballistic galvanometer also it is, but small modifications because what is the requirement? There is no controlling torque. Here there is no controlling torque. A spring we are using to give controlling torque. It is iron core. Iron core is rectangular when the coil is cylindrical. Now damping is the purpose. What is the damping we are using in PMMC instrument? It is eddy current damping. Similarly, the type of damping employed for galvanometer is eddy current damping because there is a core. The iron core provides eddy current damping. Eddy current damping obtained by a low resistance across the galvanometer terminals. Critical damping like that. Critical damping, over damping, how can you obtain? By connecting a resistance that is in control system zeta we are using. The zeta if is less than 1, greater than 1, equal to 1, critically damp, over damp, like that. By connecting a resistance it will obtain critical damping. A suspension. Next is suspension. The moving coil is suspended by a flat ribbon suspension which also carries current. Here we are using not controlling spring to carry the current. In case of PMMC instrument, a spring will be attached to this moving coil to carry the current. Those two springs we are using in PMMC instrument. That is the difference. There is no controlling spring in this directional galvanometer. The moving coil is suspended by a fat ribbon suspension which also carries the current. For upper suspension or lower suspension, this is connected through a silk enameled flat ribbon which consists of a small wire also inside to carry the current. The lower suspension has a negligible torque effect. There is no ribbon suspension, there is no controlling torque. Very low controlling torque is provided. Hence the galvanometer, if you shake the galvanometer or if you take the galvanometer in the lab, the pointer can easily move. You can observe that the pointer, why it is moving freely when you shake the galvanometer or when you turn the galvanometer, the pointer easily move. The galvanometer is a very sensitive instrument, hence we have to use very carefully. This is the construction regarding directional galvanometer. Here one mirror we are using to show indication a light is projected. This beam of light reflected on a scale upon which deflection is measured. A mirror is attached to that rotating part. The zero setting also there. The zero setting we are using for galvanometer to set the zero condition. If the pointer is not in zero condition, initially galvanometer will be in zero condition, and this is the some values are there around 0 and behind 0 and right hand side, left hand side, both sides some values are there. This is a construction regarding PMMC instrument. Similar to that, it is a D'Arsonval galvanometer. Now coming to ballistic galvanometer. Ballistic galvanometer also same. Similar to that, again the same we are explaining. The ballistic galvanometer used for measurement of quantity of electricity passed through it. Quantity of electric charge means it's a current. How much current it passes, according to that it show galvanometer condition. If there is no current through galvanometer, then it show null condition. The ballistic galvanometer reads the charge directly. That means whatever be the charge it flows, it deflects. Due to flux linking with the such coil we are using a small difference for that. Ballistic galvanometer is used in conjunction with the such coil. A such coil is wounded for a number of turns. You can see this such coil. This is the such coil of ballistic galvanometer, where we want to measure the current, the measurement of current. That such coil will be placed. After that it is connected to a small spiral springs or flat ribbon. This is the construction difference between D'Arsonval and ballistic galvanometer. Ballistic galvanometer we are using in bridges also. A small springs, spiral springs we are using, spindle jewel bearings. It is similar to PMMC except such coil. Well, construction of ballistic galvanometer. The construction of ballistic galvanometer is similar to D'Arsonval type galvanometer, but basic difference between that is ballistic galvanometer used for magnetic measurements, whereas D'Arsonval galvanometer is used for electrical measurements. That is the very important point, is ballistic galvanometer is used for magnetic measurements, whereas D'Arsonval galvanometer is used for electrical measurements. That is the difference. What is the purpose? It consists of U-shaped permanent magnet similar to PMMC instrument. While explaining the PMMC instrument in unit 1 also, the PMMC instrument is similar to D'Arsonval galvanometer or ballistic galvanometer, like that we explained. But there is some modifications. Control springs we are using in PMMC instrument for this coil. Here a such coil is there. What is the purpose of such coil? Is connected to fix the two spiral springs. Whenever flux linked with the such coil, an EMF induced in it, hence spring carry the current from the such coil, which is responsible for the deflection. Such coil is placed where we want to measure the magnetic flux. Suppose a motor stator is there. When conductors are supplied with a supply, three-phase supply or single-phase supply, when three-phase supply is given, three-phase rotating magnetic field will be produced in case of induction motor. If you want to measure the flux, the such coil is placed inside of the stator or wound between inside of the stator. After that, whenever magnetic flux flows through this such coil, an EMF will be induced. That EMF will be connected to ballistic galvanometer. Ballistic galvanometer measures what is the magnetic flux inside of that mission. It's working. Ballistic galvanometer, how it works? Ballistic galvanometer, the measure system should show deflection after all the charge current passes through that, because a moving system should show deflection after the total current passes through it. The total charge passed through the coil is proportional to the EMF induced in that coil. Similar to that D'Arsonval galvanometer, constructionally working also same, but one such coil is the difference. The such coil is connected to ballistic galvanometer BZ. This purpose of such coil is to give an EMF that flows as current. But in case of bridges, when the galvanometer shows zero condition, we are taking the readings. But here the galvanometer shows some reading that we are considering. That is the difference. Coming to equation of ballistic galvanometer, that is motion equation of galvanometer, ballistic galvanometer. This is also known about, it is also known as theory of ballistic galvanometer. Theory of ballistic galvanometer, it is also called. Equation of motion explains the theory of ballistic galvanometer. If you want to explain the theory of galvanometer, you have to draw the diagram working. After that, you have to derive the theory of ballistic galvanometer, that is equation of motion or motion equation, how the pointer shows some motion. Theory of ballistic galvanometer. The motion system of ballistic galvanometer deflects only of charge passed through it. Already we know that when the current passes through the galvanometer, then only it deflects, because the controlling springs and coil, whenever current flows through the coil due to motoring action, that is a torque will be induced in the coil, deflecting torque, that torque moves the pointer. Because suppose q is the charge to be measured, q equal to integral, to derive that we are considering the total amount of charge to be measured, q equal to integral I dt, from that I equal to dq by dt, where theta is known as deflection in radians, d is the damping constant we assumed. The motion equation of galvanometer can be determined by amount of charge passed through it. The charge is given by integral I dt. From that, current I equal to dq by dt. The change of charge, rate of change of charge is nothing but current I equal to dq by dt. You will get. Let we are assuming some terms related to ballistic galvanometer. Let theta is the deflection radians. Everybody knows that theta is deflection angle. D is the damping constant, J is momentum of inertia, K is controlling spring constant, G equal to displacement constant. The equation of motion of the coil is given by, according to control systems we are using for second order system, what is the equation of motion is J d square theta by dt square plus d d theta by dt plus k theta equal to Gi. From that we can replace, in place of I, this one I equal to dq by dt, we replaced in this equation, in above equation, d square theta by dt square plus d by j, divide both sides with j, we will get this equation, d square theta by dt square plus d by j d theta by dt plus k by j theta equal to g by j d theta by dq by dt. Between the two initial values, between the two intervals t0 to t1, between two intervals there is no motion of the coil of the galvanometer. Integrating the above with respect to limits of t0 to t1 gives rise to integral t0 to t1 d theta square by dt square plus d by j d theta by dt plus k by j theta equal to g by j dq by dt. You will get, integrating we are applying the limits for left hand side only. Why we are applying means, between the time interval t0 to t1 there is no motion of the coil until from some current will flow through the galvanometer, then only the motion will occur in galvanometer. That means from t0 in zero condition to some initial value current flows through that, then only deflection will come. Now we are integrating with the limits t0 to t1. But the deflection theta remains 0 during t0 to t1. Then the equation of motion becomes d theta by dt equal to g by j q. In the previous equation, now this terms become 0 and g by j equal to q. D theta by dt equal to g by j into q, you will get one equation. After passing the charge, after completing interval 1, no current passing through the coil of the galvanometer, and hence the deflection torque is 0. This equation of motion after that, it is j dt d square theta by dt square plus d theta by dt plus k theta equal to 0. The solution of this differential equation is theta equal to a e power m1t plus BE power m2t, where a and b are the constants, m1 m2 are the roots of quadratic equation. The roots can be obtained by using minus b plus or minus b square root of b square minus 4ac by 2a. As the damping is very small, the damping torque is very small because a less current will be flows through the core, hence the damping torque also very small. The damping constant is very small, hence d square minus 4jk in this equation, d square minus 4jk negative, but the roots are imaginary in nature. From that, the solution of second order differential equation having complex conjugates of the roots, that is damped sinusoidal oscillator, is given by theta equal to e power minus d theta by 2 tau d sine square root of 4ac minus b square by 2a t plus alpha. This is the equation of motion regarding ballistic galvanometer. This is the construction regarding ballistic galvanometer. The constructionally it has controlling springs, whereas directional galvanometer does not have any controlling springs and iron core search coil. Additional search coil is there for ballistic galvanometer. Next is very important instrument, that is flux meter. Flux meter is used to measure the magnetic flux, total magnetic flux passed through some area, that is flux meter. A flux meter is a ballistic galvanometer and connected with a search coil. Similar to that, a flux meter is a small special type of ballistic galvanometer in which the controlling torque is very small and damping is heavy. Controlling torque is very small. Silk threaded suspension we are using for ballistic flux meter, hence it is damping torque is heavy where controlling torque is very low. The construction of PMM flux meter is similar to PMM's instrument. It consists of N and S two magnets. Between two magnets, a former, there is no former here, no former for flux meter. A coil of small cross-section area suspended from a controlling spring provided by a single silk thread. Silk thread we are using. Inside of silk thread there is a conductor. So through that the conductor, the current will passes through coil, moving coil it is. The coil moves in a narrow gap of a permanent magnet. There is no controlling springs. There is no controlling springs in flux meter. The current is injected to the coil through very thin annealed silver springs. Only small spring is used to inject the current only. To inject the current only we are using a small spring. The pointer is fixed to the moving system of flux meter and scale is calibrated in terms of flux turns. The pointer is fixed to the moving system of the flux meter, that is PMMC instrument. Similar to that, a pointer is fixed to the moving system that shows directly what is the amount of flux in terms of flux turns. As controlling torque is minimum, the pointer takes time to come back to zero position. Because controlling torque is zero, what is the purpose of controlling torque? To move the pointer from final deflection position to, suppose the pointer moved due to some flux, after that it reached to zero due to controlling spring, but the spring is not it is absent in flux meter. As controlling torque is minimum, as the controlling torque is minimum, pointer takes some time to take zero position, but readings may be taken by deserving the difference between deflected and beginning. From the beginning and ending we are considering, from that to how much deflection is there, that will be taken, because the controlling torque is zero here in case of flux meter. Suppose the flux meter moved for a small flux 0 to some value 10 Weber turns. From 10 to 20 we have to calculate the number distance between this is 20. 20 minus 10 gives 10 milli Webers or Webers, like that we can measure, because the controlling torque is absent in case of flux meter. The next is the resistance of such coil is connected to flux meter must be small. The coil such coil also resistance having very small. Theory of flux meter similar to ballistic galvanometer. The theory of flux meter, for that what are the various parts, if you know, all the parts will be considered. N is the number of turns in such coil, N is the number of turns in such coil, RC and LC are the resistance of such coil and inductance of such coil. RF is flux meter resistance, inductance of flux meter. Phi equal to flux linking with such coil. I equal to current in the circuit at any instant. Eta is the deflection of instrument at any given instant. These are the various terms we assumed similar to derive the equation of motion or flux equation, motion equation of flux meter. The equation of motion similar to that, the equation of motion is given by Tj plus Td plus Tc equal to Td, deflection torque, where J is moment of inertia, torque due to moment of inertia, and D is damping constant, damping torque, and Tc is controlling torque, Td is deflecting torque, where G is the displacement constant. From that control system equation for second order spring and mass balance, if you consider J d square theta by dt square plus d d theta by dt plus k theta equal to Ga. That is the equation of motion. Let controlling torque is very negligible, small, that is also air friction damping also small in case. Air friction damping is employed for flux meter because there is no air friction damping is employed for flux meter. There is no core here, there is no core. Whereas DR Snell galvanometer, ballistic galvanometer, there is a core. Due to the core, PMMC instrument also core having. Due to that core, this core electromagnetic damping is possible. That is eddy current damping is possible. Two torques are equal, the negligible is small, and also air friction damping is also very small. Therefore, the equation of motion can be written as this becomes 0 and this becomes 0 because there is no control spring, there is no less damping torque, there is no damping torque because there is no core. Therefore, the equation of motion is J dt d square theta by dt square equal to Gi. Make it as the equation number 1. After that, as D and K are both are 0, we can write this equation. The EMF due to any change in flux linked with the search coil is because we connected the search coil wherever we want to measure the flux. The search coil is connected wherever we want to measure the flux. These two terminals are connected to search coil. Now the EMF due to any change of flux linked with search coil is EC equal to N d phi by dt. According to Faraday's law only, the EMF will be induced in search coil whenever the flux link with search coil. Hence we can say that E is equal to N d phi by dt. N d phi by dt. Let d theta is the change in deflection, theta 2 minus theta 1. D phi is the change in flux, theta phi 2 minus phi 1. From that equation 1, it may be proved that G d theta equal to N d phi. If you equate this and this, G d theta equal to N d phi by, then from this d theta equal to N by G d phi. This is that means theta is proportional to current, direct deflection of proportional to current. The advantages of flux meter as compared to any other instrument, the advantage is that in industries the advantage of flux meter, the industrial form of flux meter is portable. The scale is directly calibrated in terms of Weber turns because the flux measurement flux unit is magnetic flux unit is Weber. In terms of Weber turns, it is connected. Number of turns on such coil we have to divide to get magnetic flux. The indication of the meter is independent of the time taken by the flux linkages. Disadvantages are there as the flux meter is less sensitive and accurate than ballistic galvanometer. It is more accurate than ballistic galvanometer. These are the small differences between ballistic galvanometer and flux meter. Whereas flux meter controlling torque is very small, whereas ballistic galvanometer controlling torque is high because no spring in flux meter. Hence ballistic galvanometer, the spring is, we are using springs, two controlling springs, and controlling torque is high. Heavy electromagnetic damping in flux meter, there is no electromagnetic damping. There is no electromagnetic damping for flux meter, not heavy. It is a electromagnetic damping is there in ballistic galvanometer. No electromagnetic damping, no eddy current damping. Damping torque is very small in case of flux meter. Less sensitive it is more sensitive, it is less accurate, it is more accurate. Ballistic galvanometer, the deflection is independent of time taken by the flux linkages. The deflection is depends on time taken by the flux linkages. These are the small differences between flux meter and ballistic galvanometer. If you know the construction in flux meter, there is no controlling spring, hence controlling torque is also small. In case of ballistic galvanometer, a controlling spring is attached to the spindle. These are the small differences between ballistic galvanometer and flux meter. Chapter name is magnetic measurements. What are the magnetic measurements? Electrical and magnetic phenomena is closely related with each other, because due to electrical current only flux will be produced, due to the flux only EMF will be induced. That is, electrical and magnetic phenomena are closely related to each other. The operating characteristics of electrical machines and apparatus and instruments are greatly influenced by the properties of magnetic materials what we are using. Hence in the introduction only I explained what is the importance of magnetic measurements. Magnetic measurements are used to know the properties of magnetic material where we are using in missions. The magnetic measurements plays vital role the working condition of a mission. If the mission is not used accurate or ferromagnetic material, inaccuracies are there inside of a stator, the motor will damage easily after some short time. That means that knowledge of magnetic measurements has importance while designing or manufacturing of electrical equipment. Designing and manufacturing equipment, magnetic measurements are important. What are the tests to be conducted? These are the very important one. Different types of tests to be conducted for ferromagnetic materials. The tests are to eliminate inaccuracies in ferromagnetic materials. If any BH loop, the BH loop or hysteresis loop will be like this BH and BH curve. If any inaccuracies are there, the BH curve will not be similar. It will come in this side, or the negative side and positive side BH loop will be vary. If it is not like this BH loop or hysteresis loop, the ferromagnetic material may be not useful for missions. Hence we are conducting so many tests. One is ballistic tests. These are known as DC tests. DC test, it is also known as DC tests. DC tests are used to measure the BH curves and hysteresis loops of ferromagnetic material, whereas AC tests are used to measure the iron loss. Iron loss or depends on frequency. Hysteresis and eddy current losses depends on frequency. Hence we are using AC tests. Steady state tests are used to measure the, these tests are employed to for obtain the magnetic value of flux density in air gap of a magnetic circuit. To find air gap flux, we are using steady state tests. Now what are the methods to determine BH loops? That is DC tests. Ballistic tests are DC tests, those are known as DC tests. The BH loops or hysteresis loops can be found by two methods. One is method of reversal, another one is step-by-step method or six-step method. In method of reversal and step-by-step method seems to be same, but according to method of reversal, one reversing switch we are using in method of reversal. 20 times we are reversing and forwarding and reversing, then it goes to recycling state. After that we are measuring the flux density. On step by step method we are gradually increasing by number of steps. Let us see how the circuit all will be. In method of reversal, a ring specimen is used. Let us see the circuit diagram. In method of reversal, we are using a ring specimen. A ring specimen means forms a solenoid or toroid. It is a toroid because solenoid will be like this. It is a toroid. A ring specimen we are using. In that ring specimen, number of turns are there. Magnetic winding this is the magnetic winding, and this is search coil winding. The search coil which is connected to ballistic galvanometer BZ, and the case switch is provided to see the reading of ballistic galvanometer, and the case switch is provided to see the reading of ballistic galvanometer we are using. Such coil is placed in between number of turns which are used to measure the magnetic flux. In this material, the BH curve is accurate or not. Inaccuracy is there, the BH curve will differ. It is the one part of BH curve or hysteresis loop. In another part, hysteresis loop will be like this. This is the BH curve, the curve which is drawn between P and H, magnetic flux density and field strength. If you draw the curve, that is a BH curve. To draw this curve, some part we are considering. This part we can obtain while practically doing this experiment. A switch with reversing switch is that the dotted line shows positive forward and reverse condition, and a rheostat we are using to flow some current. Due to this current, a magnetic flux will be created in ring specimen. After that, we are giving a DC supply. We are giving DC supply because it is a DC test. Method of reversal is a DC test. You can see the method of reversal. Yeah, a layer of thin tape is provided on ring specimen, and such coil is insulated by paraffin wax that is wound on another tape. A such coil is wound on simply another number of windings. If you wound such coil, there may be short circuit occur or insulation may be damages. Hence, we are using paraffin wax is provided for such coil. Another layer of tape is put on the such coil, and the magnetizing winding is uniformly wound on this tape. This test as shown in figure previously what we studied. This test will be conducted because of the material which we are using. It is a ring specimen. This ring specimen may be used for construction of a motor. Before construction of the motor, the material what we are employing for motor, we are measuring the hysteresis loop and magnetic properties. After demagnetizing test, how the demagnetizing test will be conducted? By reversing the supply terminals plus and minus. If you reverse the supply, the ring specimen will be demagnetized. After demagnetizing test, start the setting magnetizing current to its lowest value to highest value. If you increase the current by the use of rheostat, then a certain magnetic flux will be created due to this flow of current in the magnetizing winding. This magnetic flux will be measured by ballistic galvanometer. Now the number of turns on magnetizing winding is number of turns on ring specimen is N. Ni by L gives magnetic field strength inside of ferromagnetic material, where N is the number of turns in magnetizing winding, I is the magnetizing current, I is the magnetizing current, and L means mean circumference length of specimen in meters. From that, we are measuring BH curve. It is a BH curve. For a small field flux, we can obtain H1. For a small flux density B1, we can obtain H1. Similarly, B2 and H2, B3 and H3. If we join all these points, we will get a BH curve. To determine BH curves and hysteresis loop of a ferromagnetic material, if there is a inaccuracy in this ring specimen, the ring specimen is the ferromagnetic material used for machines and electrical machines construction. Similarly, step-by-step method. In step-by-step method, the circuit diagram will be how it seems to be similar to that. A ring specimen, we are using number of magnetizing turns. After that, a search coil or calibrating coil it is a search coil. A calibrating coil in the sense to calibrate it is working or not properly, or to check the error, calibrating coil it is. The calibrating coil is connected in series with search coil to adjust the current, to give more uniform flux, and small current enters by varying this potential divider as DC supply we are applying initially. When the switch is S1 is closed and ammeter is connected, to close and open we are using the switch, DC supply will be disconnected and connected, and S2 is the switch we are using to vary the potential divider arrangement. Here we are using number of steps, hence it is known as step-by-step method. By step-by-step method we are increasing the magnetic current I through magnetizing winding, hence the search coil measures different magnetic flux directly. It is a ballistic galvanometer, and a switch is provided across the ballistic galvanometer because it is a sensitive instrument, hence we are using the switch. This resistance used to regulate the current through search coil. If a huge current will flow, the search coil will be damages the ballistic galvanometer, hence we are using protective resistance it is. Coming to the theory of that step-by-step method, the circuit for this test as shown in figure previously, you know that the magnetizing winding is supplied through a potential divider having a large number of tappings. A large number of tappings are provided. This magnetizing current will be provided by potential divider. When the switch is at different positions, different voltages will be applied. By varying this resistance, a current will enter to the search coil. According to search coil inductance also, a current will enter to the ballistic galvanometer. The ring specimen before testing it is demagnetized. I already told you what is demagnetized. Demagnetized means reversing the switch, reversing the supply terminals plus and minus to the test. The plus and minus will be reversed. The plus and minus will be reversed. Instead of plus we are giving minus terminal and plus terminal. Then the current will flow in opposite direction, and it will completely demagnetize. When the current flow in different direction, the magnetic field direction will be opposite to previous one. Hence it nullifies the previous magnetic field. Before conducting test, it should be ensured that the test to be carried out on magnetic material, it should be nullified. Magnetic flux will be inside. It is similar by by tapping the switch S2, set tapping 1 and switch S1 is closed, and this there is a small current in the flux density from 0 to B1. 0 to B1 a small flux density will come. This is value can be observed from the deflection of ballistic galvanometer. That is directly we can, it will give magnetic flux density in terms of Weber turns. By taking the value of magnetizing current, the corresponding H1 will be calculated as H1 equal to Ni by L. Magnetic field strength is for a toroid. What is the H1? Ni by L, where N is the number of turns, I1 is the current, L is the mean circumference of that. The switch simultaneously changes to tap position 2. Similarly, we are measuring H2. Similarly, the switch will be changed to tap position 3, 4, 5 like that. So many values will be taken. From that H is calculated, H1, H2, H3, H4. Similarly, B2 can be obtained by the change of a switch B1 plus delta B, change in the flux density. You can calculate change in flux density. The B2 value will be obtained. If you calculate 1, that means that it is a ballistic galvanometer we are using. It takes some time to go 0 position. The ballistic galvanometer takes some time to go 0 position. To reach 0 position it takes some time, Hence we are adding with previous value. If you want B2, B1 plus delta B. This graph will be shows hysteresis, one part of hysteresis loop. If you apply the negative flux, you will obtain next part. Similarly, magnetic measurements will be carried out. If you apply the negative supply for this, if you conduct the test, you will obtain BH curve like this in positive supply and negative supply. Similarly, if you change the voltage level, you will get saturation level, all this, the BH curve will be like this. If the curve is differed, then the material may not be useful for electrical machine manufacturing. This is about simply what is magnetic measurements, what are the instruments, what are the tests. And another one is there, iron loss. It is very simple. Iron loss depends on AC we are giving for different material, magnetic materials. From that wattmeter we are obtaining hysteresis loss and eddy current losses. Hysteresis losses and eddy current losses can be found. These AC tests are used to find iron loss. Iron loss means when ferromagnetic materials are subjected to an alternating current, alternating flux will be produced that causes hysteresis effect on eddy currents. Eddy currents are induced in a material due to a flux linked with that material. The hysteresis loss is given by that formula pH equal to KHF Bmax power K watts per meter cube or watts per kg, where KH is known as hysteresis coefficient of given material, F is known as frequency of alterations or frequency of supply what we given, Bmax is the maximum flux density, that is Weber per meter square, K is Stimming coefficient, its value varies from 1 to 2, whereas eddy current loss is given by these losses depends on shape of the variation of the flux. Eddy current losses, a sinusoidal flux means eddy current losses will be varies. Frequency and maximum flux density of magnetic field to which the specimen is subjected, eddy current losses will be. Eddy current losses also depends on frequency, whereas hysteresis loss also depends directly proportional to frequency. It is square of frequency. Eddy current losses will be, where K is known as eddy current loss constant, Kf is known as form factor of alternating value of flux. These are the two losses we are measuring by using AC testing. Simple manner how the AC tests can be found, can be conducted on a ferromagnetic material means wattmeter method, bridge method and potentiometer method we are employed. Three methods. Whatever be the material we want to calculate the iron loss, it may be formed into Epstein square or Lloyd square. Epstein square it form a rectangular shape. In the form of strips, the magnetic material will be a wattmeter is connected, pressure coil and current coil, and supply will be given for that. From that here we are using electrostatic voltmeter, a simple setup for this measurement of iron losses. This is all about magnetic measurements and instruments. What are the tests, AC and DC, and steady state test. Three types of test will be carried out. Now coming to the syllabus: ballistic galvanometer, equation of motion, flux meter, construction, comparison, determination of BH loop by using method of reversal or 6-point method. These are two important tests. And AC testing of bar samples, iron loss of bar samples can be found by the use of Epstein square shape. That is about magnetic measurement syllabus regarding for third year electrical measurement subject.